In today's topics, optimization, this one, introduction to optimization. On this one, today we are going to introduce some basic concepts of mathematical applications like matrix algebra, vector space, linear algebra, which are required for us. Those tools are required for solving the problems on the optimization techniques. The first question what comes to us is that what is optimization? Basically, we say that optimization is a technique, is a mathematical application through which we can maximize or minimize a function. The function may be of one variable or may be of several variables, and when we are optimizing it, that is when we are maximizing or minimizing the function, they may have subject to certain constraints. Just like if you see this particular table, if you see, go through this one. In this table, what we have done, some machines are there. If you see M1, M2, M3 machines are there. These machines are producing some products P1, P2, P3 and P4, and per hour how much production rate that we are telling, that for machine 1 for producing P1 what is the time required in terms of hours, these are given, and total time available per week also is given. Unit profit for producing one product is also given, like for P1 unit profit is 7.5, for P2 it is 4.6, like this way. If you see, if we assume that xj be the number of units produced for product j. In this case, of course, it is per week. I am talking about the per week. Xj be the number of units produced for product j. In that case, what actually I have to do? For product 1, basically I am producing x1 quantity. For product 2, I am producing x2, like this way. So, obviously, our aim is to maximize our profit always. So, I can develop or formulate a mathematical model for this table like this way. Maximize z equals 7.5 x1 plus 4.6 x2 plus 9.2 x3 plus 5.25 x4. So, this is actually our profit function, because I am producing x1 quantity of product 1 whose profit is 7.5. Similarly, for product 2 I am producing x2 quantity whose profit is 4.6 per unit, like this way. So, I want to maximize the value of this subject to certain constraints. What are the constraints? Subject to, my constraint is for each quantity of item, how much time it takes and how much total time available to us, or in other sense you can tell 2.7 x1 plus 3 x2 plus 4.6 x3 plus 3 x4, this should be less than equals 3000. Similarly, for machine 2, 2x1 plus 7x2 plus 2x3 plus 5.1 x4 should be less than equals 9500, and 7.5 x1, sorry, it should not be 7.5 x1, 2.4 x1 plus 4 x2 plus 6.1 x3 plus 3 x4 less than equals 6300. So, if you see, our basic aim is I want to find out how much quantity of each product should I produce per week, so that my profit will be maximum. So, for that one I am formulating the model like this way. My profit function is this and subject to these constraints. So, once I am writing this, basically what is the job of optimization technique is that how to find out the solution of this type of model. So, basically through optimization technique what we will try to learn is that how to maximize or how to minimize a function subject to certain constraints. If you see, instead of unit profit, I have written here unit profit. If I write down this portion as unit cost, in that case, instead of the maximization problem, obviously I will try to minimize my function, and in that case your maximize will be reduced, will be replaced by minimize. So, the problem may be maximization problem, the problem may be minimization problem, depending upon what the data are available. So, we want to learn the techniques through which we can solve this kind of problems. Basically, if you see George Danjid he developed this optimization, first optimization technique in 1940s to solve some problems related to military applications. That was the first thing he developed, which we call as the linear programming problem, and that was the first optimization technique which was developed at the beginning. After that, lot of optimization models, techniques have been developed for solving different types of problems, and these are widely used nowadays in operations research, artificial intelligence, computer science, and obviously needless to say in industry it is being widely used and which is helping a lot to the industry people. Through these optimization techniques, we try to solve various kind of problems. I can list the problems. One we call as the linear problems, where in the linear problems what we say, the optimization function basically should be linear. Whenever the optimization or function or the constraints are linear functions, then those type of problems we call it as the linear functions. Whereas, there is other type of problems which I call nonlinear problems. In nonlinear problems, whenever the optimization function or the constraints are nonlinear in nature, then those problems we call it as the nonlinear problems. We have the other type of problem, that is we call it as discrete. In discrete case, what happens? The value of the variable will take some discrete integer values. Just like if you see, whenever I try to find out or make the class timetable for teachers and I am allocating subject to different rooms, always they will take some integer values. Or in a hospital, whenever I am giving scheduling duties of the nurses, those are taking the discrete values. This kind of problems we call it as the discrete problems. There is another type which we call as continuous problems. In continuous, it can take any value, any real value can be taken over there, and in this case anything whatever you do, it can take 1.5, 1.10, something like this way, any real values it can take. So, we can categorize our problems linear, nonlinear, discrete and continuous. And for each type of problem, we have several different optimization techniques. We will go through one by one all these things. Of course, we will start with the linear problems initially, and after that we will go to the nonlinear and other type of problems also. Now, let us give some introduction, as I told initially, to the basic mathematical tools which will be required to us. You may know everything, but in brief we will tell the things what is required or which we will be used afterwards in this lecture. The first one is matrix algebra. In matrix algebra, actually if you see, if you have n cross n matrix, this n cross n matrix is, we say, is an arrangement of m n objects, is an arrangement of m n objects. These objects may be distinct, may not be distinct, and you are placing these m n objects in m rows and n columns in a particular form, then we call it as a matrix. So, whenever we are defining this m cross n matrix is basically nothing but a arrangement of m n objects in m rows and n columns, and we write it in the form like this. A11, A12, A1n, A21, 22, 2n, AM1, M2, Mn. So, we have total Mn objects. We say that the matrix is of order m cross n, since it has m rows and n columns. So, its order is m cross n, and whenever m is not equals n, we tell that the matrix as rectangular matrix. When m is not equals n, we call the matrix as rectangular matrix. Now, each object a I j, basically this object a I j is, we call it as an element of the matrix. A I j, the object a I j is an element of the matrix, that is the element on the ith row and on the jth column. This element we call it as the element of the matrix. Whereas, if you see A11, A22 like this way, A n n, that is these diagonals A11, A22, A m n, sorry, A m n, this one we call it as the diagonal elements. These elements we call as diagonal elements. Now, Rho matrix, just some definitions. A matrix of order 1 cross n. If I write down a matrix of order 1 cross n, that is 1 row and n columns, then we call it as the Rho matrix, and we write it as A11, A12 like this way, A1n. So, this one is a Rho matrix. Similarly, you can define the column matrix. In case of column matrix, what happens? We have a matrix which takes the form of m cross 1, that is m rows and 1 column, then we call it as the column matrix, and it takes the form of this one A11, A21 like this way, it will go up to AM1. So, A11, A21, AM1, this one we are calling as the column matrix. Next comes square matrix. If you have a matrix of order m cross n, where m equals n, that is number of rows and number of columns are equal, then we call that matrix as a square matrix of order n. Whenever you are having the number of rows and number of columns are same, then we call that matrix as the square matrix. We can write down like this. So, this matrix is the square matrix which has n rows and n columns. Next, there comes null matrix. You have the matrix A equals A I j, the order is m cross n. If A I j equals 0 for all I and j, if A I j equals 0 for all I and j, then that matrix we call it as the null matrix. I can write down something like this: 0 0 0 0 0 0 and all are zeros. So, this matrix whatever I have written is a null matrix of order 3, or it has 3 rows and 3 columns. Next, diagonal matrix. In a square matrix, please note that in a square matrix, not rectangular matrix, that is square matrix means I am writing A I j n cross n. If A I j equals 0 for I not equals j, that is except the diagonal elements if all the elements are 0, except the diagonal elements if all the elements are 0, then that matrix we call it as the diagonal matrix. Just like you can, for example, you can write down this matrix . This matrix, if you see, this one is the diagonal matrix, except the diagonals all other elements are zeros. So, this is a diagonal matrix. Next one is the identity matrix, or sometimes we call it as the unit matrix also. In a diagonal matrix, if the diagonal elements are 1, then that matrix we call it as the identity matrix. That is, these diagonal values of these diagonal elements, if this is equals to 1, then we call it as the diagonal matrix, and this we may write it like this. This matrix where all the elements are 0 except the diagonal elements, and this identity matrix we usually denote it by I, which is the diagonal matrix, or sometimes we call it as the identity matrix. The next one is upper triangular matrix. This upper triangular matrix is a square matrix where all the elements above and on the right of the diagonal matrix are non-zero, or in other sense you can tell all the elements below the diagonal elements are 0. In any way you can represent it, either all the elements above the diagonal elements and the right of the diagonal element are non-zero. So, for an example, you may say something like this: a matrix, you consider this one, so if you see this, in this case all the elements above the diagonal elements are non-zero, and this side all the elements below the diagonal elements are 0. So, this one we call it as the upper triangular matrix, and similarly you can define the lower triangular matrix also. The lower triangular matrix can be defined like this. I am directly giving one example, it will be clear to you, I think. If you see this, then all the elements above the diagonal elements are 0. All the elements above the diagonal elements are 0 and all the elements below these diagonal elements are non-zeros. So, this kind of matrices we call it as the lower triangular matrices. Some basic matrix operation like addition, subtraction. So, first come to the addition and subtraction. In addition and subtraction, what happens? You first consider a matrix Aij. The size is of course m cross n. There is another matrix Bij whose size is also m cross n. I am considering a third matrix C, elements are Cij, and this is also will be order this. Now, whenever you are writing C equals A plus B, it means one element ijth element Cij of the resultant matrix, this should be equals to Aij plus Bij. Similarly, whenever you are writing C equals A minus B, it implies Cij, this is equals to Aij minus Bij. So, basically you are making term wise addition or term wise subtraction for performing the addition or subtraction operation. One thing should be noted that whenever you are performing the addition or subtraction operation, the order of both the matrices should remain same, it should not change over there. Next comes matrix multiplication. In matrix multiplication, what happens? Whenever you try to multiply two matrices, the first thing required is that either the number of columns of the first matrix should be equals to number of rows of the second matrix, then only we can multiply two matrices, otherwise we cannot multiply the matrices. So, again if you consider the matrices A equals Aij say, whose order is m cross n. Let us take another matrix B, which is equals to Bij of order n cross p, and there is a third matrix C, C equals Cij. If this is the resultant matrix, the order of this one will be m cross p, that is number of rows of the first matrix into number of columns of the second matrix. This will be the order of the resultant matrix. So, if you write down C equals this Cij m cross p, which is nothing but again your product of two matrices A and B. I am just writing this to show you in details. You have A11, A12, A1n. Like this way, you are having in middle ith row I1, I2, In, and at last you are having A M1, A M2, A Mn. This is the matrix A, and you are having the matrix B. Similarly, B11, here I am writing B1j, B1p, B21, B2j, B2p. Similarly, Bm1, this should not be n cross p, so it will be n, Bnj and Bnp. So, whenever you are having two matrices like this, just you see this one, whenever you are matrices, you have the matrices like this way. In that case, what happens? Your Cij is nothing but the element wise product and then sum of these two rows and columns, whatever I am marking. That is a I 1 into B 1 j plus a I 2 into B 2 j dot dot like this way plus a I n into B n j. In writing, we can write down a I 1 B 1 j plus a I 2 B 2 j, like this way it will go, and a I n into B n j, or in other sense in summation form k equals 1 to n a I k into B k j. So, this is the product of elements. Like this way I can find out each element of the resultant matrix C Cij using this formula. If you take one example here, suppose you have the matrix A, small matrix, very 2 cross 2 matrix, 4 0 6 0. You have the matrix B 0 0 and 5 7. If I find out the product using our procedure, then first term 4 into 0, 0 into 5, it plus 0. So, it is 0. Like this way you will find A B is 0 0. Similarly, your B A, if you calculate, B A also you can calculate, because number of rows and number of columns of both the matrices are same. From your B A you can calculate as 0 0 62 and 0. So, once I am calculating A B and B A, one thing is very clear, that is, it is not necessary that A B will be always will be equals to B A. It may be equals, it may not be equals. Another thing is that if product, if you see here, although A and B two non-zero matrices, the product of these two are 0. So, if product of two matrices A B equals 0, it does not necessarily imply that either A will be equals to 0 or B equals to 0. We should note this one. Similarly, if you are having A B equals A C, it does not necessarily imply that B will be equals to C. It may hold, it may not hold. So, these things we have to keep in mind. The next one is transpose of a matrix. The transpose of a matrix is basically whenever you are interchanging the rows and columns of a matrix and the resultant matrix, we call it as the transpose of the matrix. That is, if you have a matrix A, which you are telling as Aij m cross n matrix, suppose you are having A11, A12, A1n, A21, A22, A2n and AN1, M1, A M2, A Mn. This matrix is there. So, if I write down A transpose, then A transpose will be by simply by interchanging the number of rows and number of columns of this matrix. Number of rows and number of columns of this matrix means here it will be A11, A21 and then A M1. This column is being changed as row. The next one will be A12, A22 into A M2 and the last one will be A1n, A2n, like this way AMN. So, transpose of a matrix is nothing but whenever you are interchanging the rows and columns of two matrices, then we call it as the transpose of a matrix. Transpose of a matrix has some properties like A transpose whole transpose. If you take, you will get back the original matrix itself. A plus B transpose, this is equals to A transpose plus B transpose, and A B transpose, this is equals the opposite way it will go, that is B transpose into A transpose. So, we will use these things for finding the solutions. You will see how we are actually using all these properties afterwards, how you are representing, formulating a model, converting in terms of matrices, you are trying to find out the solutions. So, we are going through that part. The next one is determinant. Consider a matrix A equals Aij of order n cross n, that is, it is a square matrix. Then det A we write denoted det A or this notation, whatever you want you can use. Det A will be, we write like this way. A2n, and lastly so, det A is this one. For example, if you have a determinant of order 2 only, that is A11, A12, A21, A22, I can evaluate it and I can obtain the value, that is this element into this element minus this element into this element. So, A11, A22 minus A12 into A21. Like this way, you can evaluate one determinant and you can find a value. The next one is minor. The minor of an element Aij, obviously of a determinant A, I am talking about with respect to A, is the determinant of order n minus 1, is a determinant of order n minus 1 by omitting the ith row and jth column. So, basically what is a minor? You have this determinant. If I want to find out the minor of A22, in that case I will omit the second row and second column, and I will get another determinant whose order will be 1 less. Since I have deleted 1 row and 1 column, order will be n minus 1, and that we call as the minor of the element Aij. The next term is cofactor. The cofactor of an element again is defined as minus 1 to the power I plus j into Mij, where Mij is the minor of Aij, where capital Mij is the minor of Aij. So, once I know the minor, I can find out the cofactor of any element, that is the minor into minus 1 to the power 1 plus I plus j. Next one is singular and non-singular matrix. Singular and non-singular matrix. You have a matrix A, which again I am writing as n cross n matrix of square matrix of order n. Now, we say that A is a singular matrix if determinant of A is equals to 0. A is a singular matrix if determinant of A equals 0. The matrix A is said to be non-singular matrix if determinant of A is not equals to 0. So, if determinant of A is not equals to 0, then the matrix is non-singular. If it is equals to 0, then it is singular matrix. The next one is rank of a matrix. You have a matrix A obviously A equals Aij of order m cross n. We say that the rank of A this is R if all square minors of order r plus 1 or above are singular and there exists at least one minor of order r which is non-singular, then the rank of that matrix is R. That is, all the minors of order r plus 1 whose are singular and at least one minor will be there of order r which is non-singular or whose determinant does not vanish. That one we call as the rank of a matrix. Just let us take one example. You take a matrix A little bigger, this one for this matrix A, let us perform some row operations like this. One operation I will do R 3 minus 2 R 1, another one we will do R 4 minus 3 R 1. If I do these two operations R 3 minus 2 R 1, that is the first element of the third row will become 0. Similarly, the second element of the third row will become 0. Like this way you do the operations. If we go through these operations and after this I am not writing all of them because it will take time. I am just writing here the operations you will perform one after another, that is first these two, then you operate R 3 plus R 2, then you interchange the third row, fourth row, and at last you do this operation R 3 plus 5 by R 3 plus it should be 5 by 2 R 2, R 3 plus 5 by 2 R 2. These operations you do in order one after another in this order, and ultimately you will find one matrix of this particular form 1 3 2 4 1 0 0 2 2 0 0 0 0 3 3 and the last row has become 0. So, if you see this, what is the rank of this matrix now? The original matrix was this. Using row operations, we transform this matrix into this one. Here the last row is this. So, if you take the rank of this matrix will be 3, the rank will become 3, because if you take any matrix of order 4, that rank will be 0 over here, because one row is 0. So, if you evaluate the determinant, value will be 0, but if you take one matrix of size, one determinant of order 3 which will be non-zero. So, therefore, the rank is 3. So, rank is the value for which the minor has non-zero determinant or the minor is non-singular. This we call as the rank of the matrix. The next one is adjoint of a matrix. The adjoint of a matrix you have a matrix A, Aij, B and square matrix of order n. Then adjoint of A simply we write as the transpose of transpose of the matrix of cofactors of A, transpose of the matrix of cofactors of A. So, you are first finding out the cofactor of each element of the matrix A. Already we have told how to find out the cofactor, and then make a transpose of the matrix of the cofactors. That matrix, resultant matrix, is called as adjoint matrix. If you see, consider one example. A equals this, for this matrix cofactor of 2, just I will calculate 1 2 cofactor. Cofactor of the first element 2 is, you delete the corresponding row and column. So, it is minus 1 to the power I plus j, that is 1 plus 1 into this matrix. If I delete this row and column, so it will be 0 1 and minus 1 4. If you evaluate, it will become 1. Similarly, your cofactor of 3, also cofactor of minus 3, this element, this will be equals to minus 1 to the power 1 plus 2 into, take the corresponding determinant after omitting the corresponding row and the corresponding column, and you will get some value. Like this way I can find out the cofactors. So, adjoint of A, simply I can write down like this. You find out the cofactors 1 minus 4 minus 1, you can calculate of your own, and this one will come as this, and transpose of this matrix, that is, you just write down this one as 1 8 minus 3 minus 4 8 2 and minus 1 2 and 3. So, this is the adjoint of a matrix. Next come to the inverse of a matrix. The inverse of a matrix, again we are assuming that this matrix A is square matrix and it is a non-singular matrix of order n. So, A is a square non-singular matrix of order n. We say that matrix A is invertible if there exists a non-singular square matrix B. There exists a non-singular square matrix B such that a B, of course, the order of B also will be n, such that A B equals B A equals I. Then, and we denote this A inverse by adjoint of A by determinant of A. So, actually what is happening? If the inverse of a matrix exists, if it is non-singular, if it is square. Now, if we can find a matrix B of order n, square matrix B of order n such that A B equals B A equals I, where of course, I is the identity matrix which we have told earlier. Then A inverse we are defining as adjoint A by determinant A. For the earlier example, whatever we told, A inverse can be calculated as this one, 1 by 10 into adjoint A, which already adjoint A we have calculated in the earlier example as this one. This is the adjoint A, and the value of this determinant of this matrix A is 10. So, therefore, our basically A inverse becomes this one. So, this is the preliminaries about the matrix. Now, let us come to the next one, that is vector space. Basically, if you say matrices having single row or column are often referred to as vectors. That is, if I write down something like this we call as a vector of size n equals 5, or number of components of this vector is 5. If you write something like this, then obviously, this is a column vector, this one was the row vector, this is a column vector with of size 2, since it has 2 elements. If you say the vectors, whenever I am writing this A1, A2, this actually geometrically what I can say, this represents a point in 2-dimensional space. A1, A2 whenever writing, you are writing this represents a point in 2-dimensional space. When I am writing A1, A2 and A3, this represents a point in 3 dimensional space. Similarly, if you are writing A1, A2 like this way, N, AN, then we can imagine it as a point on the n dimensional space. Now, come to the null vector. Null vector is a vector whose all the components or elements are 0. We denote it something like this way. So, null vector is the vector whose all components are 0. Next one is the unit vector. Unit vector usually we denote it by the EI, is the EI, and what happens in the ith component the value will be 1, all other component value will be 0. Then we call it as the unit vector. So, when you are writing E1, that means first component will be 1, all other components will be 0. Similarly, if I am writing E2, the second component will be 1, all other components will be 0, and if I am writing En, then the last component will be 1, all other components will be 0 in this case. So, this is your unit vector. Now, come to the vector space. A set of vectors are there, you assume a set of vectors x1, x2, xn is there. This set of vectors x1, x2, xn is closed under addition and scalar multiplication. Then we say that this set of vectors form a vector space. So, if these vectors x1, x2, xn are closed under addition and scalar multiplication, then this forms a vector space. So, next question obviously comes, what do you mean by closed under addition and scalar multiplication? A vector is closed under addition means that if you take any vector or two vectors of the set and if you add these two vectors, the resultant vector should also be a member of the original set. Then we call it that it is your closed with respect to addition. Similarly, a vector is closed or a set is closed with respect to scalar multiplication means whenever you take scalar multiply any vector, the resultant vector should also be a member of the original matrix, original vector. Then we say that it is from a vector space. For example, if you try to take the examples, you take the set of all real numbers, say you take any two real numbers, you from the addition you will get another number which is in the again a real number. Similarly, any two real numbers if I take and multiply, I will get another real number. So, set of real numbers are always forms a vector space. Similarly, if I take set of all polynomials whose degree is less than or equals to n will also form a vector space. But consider the case set of all polynomials whose degree is exactly equals to n. Let us take a set of polynomials whose degree is equals to n. That means, I can write down P n equals something like this, one polynomial a1 x to the power n minus 1 like this way a n, and q n equals say minus x to the power n b 1 x to the power n minus 1 plus b n. Now, if you make the addition of these two polynomials p n plus q n, in that case you will find that you are getting one polynomial whose degree is n minus 1, but my set was set of all polynomials of degree n. So, we can conclude that set of all polynomials will degree n will not form a vector space. So, like this way we can calculate the vector space and check whether a set is a vector space or not. The next one is linear combination. A linear combination, suppose you have a vector A which is in R n, if I write down a vector n is R n, it is a linear combination of vectors say a1, a2, an. This a1, a2, an also belongs to Rn. If I can write down A equals lambda 1 a1 plus lambda 2 a2 plus lambda n an for some scalars lambda, sorry, for some lambda 2 and this will be lambda n, for some scalars lambda 1, lambda 2 and lambda n. So, a vector A is there, there is another set of vectors a1, a2, an, all of them belongs to Rn. Then if I can write down A equals lambda 1 a1, lambda 2 a2 plus lambda n an in this form, where lambda i's are scalars, then we say that A is a linear combination of the vectors a1, a2, an. In particular, if summation I equals 1 to n lambda I, this is equals to n, then this combination we call it as convex combination. Whenever this summation I equals 1 to n lambda I equals to 1, this we call it as the convex combination. For example, if you take a vector a1 1 2 3, a2 as -1 1 -1 and a3 this is equals to say 0 3 2, always I can write down a3 equals 1 into a1 plus 1 into a2 such. So, your a3 sorry, this will be a1, a3 will be a linear combination of a1 and a2. Here lambda 1 is 1 and lambda 2 is also 1. Next comes linear dependence. Again, you have a set of vectors a1, a2, an which belongs to this set of vectors a1, a2, an which is belongs to Rn is said to be linearly dependent if there exist scalars lambda I such that lambda 1 a1 plus lambda 2 a2 plus lambda n an this is equals 0, but not all lambda i's are 0, not all lambda i's are 0, then we say the vectors are linearly dependent. So, a set of vectors a1, a2, an are linearly dependent whenever lambda 1 a1 plus lambda 2 a2 plus lambda n an this is equals to 0, where all lambda i's are not equals to 0. So, for the earlier example, this example a1, a2, a3 these are linearly dependent since a1 plus a2 minus a3 equals 0 and all lambda is not equals 0. But on the other way, if lambda 1 a1 plus lambda 2 a2 plus lambda n an this is equals 0, this holds when all lambda i's are 0, that is lambda 1 equals lambda 2 equals lambda n equals 0. Then we say that the vectors a1, a2, an are linearly independent. I am just writing this, they are linearly independent. So, these two concepts are very important. One is linearly dependent, another one is linearly independent. So, linearly independent means whenever you are making the linear combination of these that is equals to 0, but all the lambda i's are equals to 0. If you consider, if I am just writing here one vector a1, another vector equals this. So, if I take lambda a1 plus lambda 1 a1 plus lambda 2 a2 this is equals 0, and this is possible only when lambda 1 equals lambda 2 equals 0. So, I can tell that the vectors lambda 1 the vectors a1 and a2 are linearly independent. Next, there comes spanning set. Again, take a set of vectors a1, a2, an which belongs to Rn. A set of vectors A1, A2, Rn is said to span or generate Rn if every vector of Rn can be written as a linear combination of A1, A2, An. That is, you are having a set of vectors. From this set of vectors, you are generating all the vectors, means any vector you take on Rn, that will be a linear combination of the vectors A1, A2, An. Then this set through which you are generating, we call it as the spanning set, and obviously this set of vectors are linearly independent vectors. This A1, A2, An, this spanning set should be linearly independent. For example, if you want to take the example, in that case, if you take the set of vectors E1, E2, En, if you take these vectors, any vector on Rn can be generated from this set E1, E2, En. So, your E1 is 1, 0, 0 unit vectors. On unity, it is 1 on the first component, all others are zeros. So, any vector A can be represented in terms of this one, that is, you can write down A equals A1 E1 plus A2 E2 plus An En. So, this is the spanning set of this. Next, there comes basis of a vector. A basis, we call it linearly independent subset of vectors which spans the Rn, which spans the vector space. In our earlier examples, E1, E2, En, these are the basis of the Rn. So, basically the linearly independent subset of vectors which spanning all the elements, all the vectors of a set is called the basis of that. For this case, E1, E2, En is the basis of this case, and along with this there is another one which we call as the dimension of a set. Dimension means number of linearly independent vectors, whatever is there, that number we call it as the basis. Now, next comes to convex set. You have a set X, the set X we call as convex set if for any point, say x1, x2, which belongs to X, if you join the line segments of x1 to x2, the line segment is also lies on X, then we say that the set is a convex set. So, you have any two points x1, x2 of X, if you join the line segment x1, x2, if entire line segment lies on the set X, then X is called the convex set. Mathematically, if I have to say, then we will say that if x1, x2 belongs to X, if I can find a point X such that X equals lambda x1 plus 1 minus lambda into x2, lambda lies between 0 to 1. If it is satisfied, then the set is a convex set. For example, if you consider, if you take a triangle, the triangle and its interior will form one convex set, because if you take any point, any 2 points inside this, if you join, that will lie also inside the triangle. Similarly, if I take a point something like this, in that case also this will form a convex set, this entire rectangular place. But suppose I have taken something like this, some figure like this, this is not a convex set, because if I take a point here, if I take a point here, if I join this line segment does not lie on the lie on this set. Therefore, this one is not a convex set. Similarly, there is just another point, that is extreme point. An extreme point of a convex set X, this extreme point of a convex set will be that point such that we cannot find two other points x1 and x2, such that if I join them, I will get the point. Or in other sense, if I have to say this point, if you consider this point, these are the extreme points, because I cannot find out any two other points which will lie over here. But if you consider this one x 1 say x 2, if you take another point x 3, although it is on the exterior, but I am finding 2 points x 1 x 2, and if I joining them, then x 3 lies on it. Therefore, x 3 is not a extreme point, whereas x 1 and x 2 is the extreme point. Thank you.